Okay, my name's Crossland. I usually describe myself as a nuclear engineer, and my specialist area is radioactive waste management. And in fact, I need to get away at 3 o'clock because I'm going to Kiev to talk about Chernobyl. But anyhow, don't need that. So I had a colleague years and years ago, and he had a philosophical bent, and he said nuclear power is a conditional good. And it struck me as being very profound at the time. But the problem is that it applies to virtually any technology you can think of. In the case of nuclear power, we don't need to look very far before we find the disadvantages. And if we look around, well, we see, obviously it applies to motor cars, to fossil fuels. You might even say it applies to the bicycle. So I think if you're going to really get into this issue, you need to start looking at details. And although the talk is labelled ethics, I'm not an ethicist, so there might be some danger of transgressing the Trade Descriptions Act, but I'll do my best. So if we look at the advantages of nuclear power, basically in terms of sustainability, there's enough uranium in the ground or even in the sea to keep us going for a very long time. And if need be, there are other technologies, fast neutron reactors spring immediately to mind, that could extend the timescale by a factor of 100 probably, and could also deploy thorium to substitute for uranium. And there's plenty of thorium in the world. Next down, NPPs, nuclear power plants, use huge amounts of concrete and steel in their construction, but because they also generate massive amounts of energy, the carbon emitted per kilowatt is actually less than it would be for wind power. And the main problem with renewables is the intermittency, of course. And there's something about that on the next, on this next slide. The blue line here, that's the wavy one at the top, shows the electricity demand on a typical winter day. And engineers from the National Grid Company must match supply and demand very precisely. If they don't, this causes changes in the frequency of the supply and ultimately a failure of the grid. And in the past, this has been done by creating a base or steady load at the bottom. And you'll see that here, nuclear we have here, but there will be coal as well on top of that. And then they bring in additional capacity, normally gas, to meet the peaks. So they effectively tune the supply to meet the demand. The problem with the renewables is that they immediately bring in intermittency to play, and that introduces additional technical challenges. So in this diagram, I've imagined that the energy supply coming from wind, solar and nuclear, I've restricted this to these three notionally. And I've arranged things so the total energy generated over the 24-hour period, that's the area under the blue line, is equal to the amount of energy produced. The problem is that although enough electricity in gross is being produced, it's not being produced at the right time. Somehow one must store electricity when it's in excess so that it can be drawn upon when there's a shortage. And for the situation shown here, the energy needing to be stored is about 50 gigawatt hours. Now at the moment, if you think of large-scale batteries or even car batteries, maybe a fraction of the car battery energy, we're typically talking about the megawatt hour range. So we're something like 100 to 1,000 times too small in terms of meeting that gap. And of course, one of the things you could do would be to increase the number of renewables so that it exceeds the demand. And then what you'd have to do is to shut down the renewables when the energy was too much, or find some other method of storing the energy. And this happens at the moment, of course, when you've got very high wind conditions. And essentially the grid have to tell people, no, shut down there, we don't need your electricity. What that does, of course, is to increase the price of electricity because you're generating electricity which isn't going to be used. Nuclear does have some ability to load fully. It's usually a few tens of percentage of full load. So you can imagine little bumps on the nuclear there going to something like 20% where the peaks in demand occur. But of course, if you're going to make use of that, to meet the actual size of the bump, the nuclear needs to be higher, because at the moment 20% of not a lot is not a lot. If you need to make it, if you're going to meet those bumps, it would have to be higher. So you also have to recognise that there will be some days when wind output will be very low. And having a significant offshore capacity and a wide geographical spread, aided by interconnections to the continent, will reduce the frequency of these gaps. But nevertheless, there will be some occasions when additional electricity will be needed from somewhere. And the National Grid Company solution to these potential shortages is what's called the capacity market, whereby generators are paid for standing by, ready to supply. So when there's a big gap, there's a big wind shortage, low wind conditions, they call on these people, right, you need to generate now. And if they fail to generate, then there are large fines imposed upon them. But otherwise, provided they can meet the request when it's generated, then they just get money for standing by and being ready to generate. Of course, what this does again is to increase the price of electricity, because again you've got plant and people standing by ready to do something when in fact there may be no need for them to do anything in the end. And that burden is borne by the electricity consumer, you and me. The general strategy for dealing with climate change is to increase electricity generation to substitute for fossil fuels. So that instead of driving around in motor cars or eating into our houses with oil or gas, we instead use electricity. What that means is that the whole scale of this curve goes up. And somehow you have to manage these peaks and also manage the uncertainty that's introduced by renewables. And that really gives you an idea, how do we go back, of why the whole problem is so difficult. I think I probably said that. Okay. So, let's go on to the disadvantage of nuclear power. It is perceived as dangerous, and it's hardly necessary to repeat the roll call of accidents: Mayak, the Windscale fire in the 50s, 4 Mile Island, Chernobyl, Fukushima most recently. The number of people killed in these events is widely disputed, but most estimate excess deaths from cancer. Part of the difficulty is that it's not people killed at the time of the accident, it's contamination, which doses people now, and then they die of cancer in 20 or 30 years' time. So you have to make some kind of estimate of these excess deaths from cancer. Most estimates for these 4-5 accidents come out at around 10,000. It is highly disputed. I think we go on to the next slide. So if you look at that 10,000 figure and compare it with other hazardous activities, we see smoking. About 7.1 million people a year die. That was a 2016 figure. Industrial accidents, 2.3 million a year, currently 100 a year in the UK. Road accidents, 1.25 million. Commercial flying. I've taken the figure since 1950 for comparison with nuclear power. And over the period since the 50s, 70,000 people have been killed by commercial flying. It's currently down to about 100 a year, and that's because of great improvements in air safety. Nuclear power, you've got your figure of 10,000, mostly from Mayak and from Chernobyl. One of the issues associated issues here is that flying accidents were relatively common. They're less common now, but by dint of scrupulous reporting and careful investigation, it's been possible to improve the safety of flying by something like a factor of 100 over the past 40, 50 years. Unfortunately, or maybe fortunately, we don't get big nuclear accidents that frequently. It's more difficult to learn from these accidents. Clearly the messages are spread around that the IAEA has a big role here to play in promulgating good practice. But one of the issues that's been picked up is the issue of safety culture, and in particular no blame reporting, so that members of staff on nuclear power plants should be, I don't say always are, but should be encouraged to report near misses, so that, you know, I nearly turned this valve rather than that valve by mistake. The management shouldn't say, I hit you with a big stick for doing that, punish you. They should say, congratulations for alerting us to a possible difficulty, because any failure on the plant is not a personal failure, it's a systemic failure, and it's the system we have to get right. So if you nearly turned the wrong valve, which could have caused an accident, that's not because of your fault, it's because the procedures aren't sufficiently clear, or the interlocks aren't in place. So that's the kind of route that's being used at the moment to try to improve nuclear safety. I think I need to go back. Yeah, so one of the issues is a large nuclear accident may be accompanied by widespread contamination, so that humans may need to be removed from an area. So I'm basically concluding that in terms of danger, I didn't want to talk about polluting from normal discharges, but we'll talk about the wider aspects of pollution from a big accident. One of the issues is that if an area gets contaminated, as at Chernobyl, as again at Fukushima, people have to be removed from those areas and not allowed to return. This is a really difficult issue, because actually even moving people from their normal way of life, displacing them. I mean, the simple case would be moving people out of hospital into a different hospital. People can die in transit because they don't have the same care that they have in the hospital. But longer term, people who have steady jobs, you've heard of the healthy worker effect. When you're doing epidemiological studies, it's always found that people who have a steady job with a regular income have better health than people who don't. They're a happy worker. If you deprive someone of their living by moving them to a distant town, you deprive them of their income and their normal way of life. And that itself can be a bigger health detriment than actually leaving them to be exposed to the radiation. This is a really difficult issue because people have a fear of contamination. You know, their immediate instinct is to try to flee from it, to get away from it. It may not be as dangerous as you think it is. One of the other points is that residents who moved away have a reasonable expectation that the area they've moved from should be completely cleared, should be completely clean before they move back again. So that's the way it was before. That's the way I expect it to be in future. It might not always be possible to do that. And so what do you do? How do you help these people? How do you help them either to go back or to find a new life? It's a really difficult issue. For me, this is probably one of the most difficult issues in nuclear power. I'm not so worried about the danger, the number of people that might be killed. I think probably the estimates are overestimates anyway. But this is a really thorny issue which people are trying to deal with, and there's no clear answer at the moment. I think the one undeniable message is that what you should do most of all is to avoid big accidents, but I think we all knew that anyway, didn't we? Right, let's move on to waste management. We all hear about radioactive waste which live for remain radioactive for hundreds of thousands of years. It's true. But over the past 40 years, people have been studying the technology of deep geological disposal. And there are technologies which now exist which allow this to proceed. And in fact, good progress is being made in Finland and Sweden as we speak. One of the main issues is in fact social acceptance, and it does appear that in the Scandinavian countries they do have a higher trust in their societal structures, in their political structures, that allow them to accept the word of experts and so on. Other countries, it isn't so strong, and it's more difficult to persuade people that they ought to be allowing this technology to go ahead. So, how am I doing for time, Andrew?
Maybe a few more minutes and then
Okay.
we can have questions.
I'll try and, yeah, I'll talk about the facility about nuclear weapons. Well, the link between nuclear weapons and nuclear power is real. It goes right back to the Manhattan Project, when many of these technologies were developed. The argument against nuclear power is that its wider use will encourage nuclear weapons proliferation by providing states, rogue states or otherwise, with the means to produce weapons material. Inspections by IAEA and Euratom provide assurance that non-nuclear weapons states don't use nuclear power to feed a weapons program. But this is not a cast iron guarantee, and we all know that states can and do manage to subvert these schemes. The technology cannot be uninvented. Individual states will decide whether they need nuclear weapons or not, whether they have the resources to, and whether they have the resources to develop them. But to me, it seems that the existence of a civil nuclear program will have little bearing on such decisions. If a state really wants nuclear weapons, it will find the means to get them. And if that means building research reactors or plutonium-producing reactors, well, they'll do that. I think the other issue is to do with dirty bombs, and to me that's more a problem with use of radioactivity more generally, in hospitals in particular, and in industry. And there's been a big effort over the past 10, 15 years to make sealed sources from these non-nuclear uses much more secure. The Americans have been way ahead on this. So I'll just finish with, so I think there's another conclusion should go above the whole of this, and this is that when it comes to energy production, there are no easy choices. There are always going to be compromises to be met. But nuclear power is a conditional good, but then so are so many other things. Nuclear power is certainly not unethical in principle, in my view. Like any enterprise, of course, so it could be operated in an unethical way. One's view of whether it's something to be encouraged or not will depend on one's values, what the social scientists call values, really your view of the world, and on how your experience of the real world, how it actually operates in practice. I don't imagine that anything I've said will get people to change their views fundamentally. My personal view, for what it's worth, is that nuclear power is, at the moment at least, an essential component of a balanced energy policy. How large a component really depends on many things, not least future developments in energy storage, and in fact the ability of nuclear power to produce energy at a reasonable cost, which at the moment it doesn't seem to. But as I said, in the end, you will have your own view. I've put my own view. There are no easy choices. Whatever you do in this situation is going to be a compromise.